We now come to chapter 5 in the textbook. This concerns hierarchical models. So these are models that we use for repeated measures data. And for the rest of this book, we'll mostly be working with hierarchical modeling. These are also called linear mixed models or multi-level models in the frequentist world. But we are going to call them hierarchical for reasons that you will see in a few minutes. So as always, there's a textbook. You can look at the online version of the textbook here, the source code that has all the code and reproducible material in this GitHub repository. And if you want a physical copy of the book, you can get it from here. I'm assuming that you've read all the chapters up to chapter 5 in the textbook and watched the lectures. If you haven't read the lecture notes, you should read them at some point before moving on to the rest of the book. Okay, so in this chapter, I'm going to start by fitting a very simple model, just very similar to the models that we've already seen in chapters 3 and 4. And then I'm going to start adding more and more structure to this simple linear model. So the example that we're going to start with is an EEG data set. So we've got a signal in microvolts. These are electrical signals that are recorded on the scalp through electrodes, and we are assuming that the data are going to be modeled as coming from a normal distribution. And we're going to start with a very simple linear model, just like the one that we had seen earlier. Here we've got an intercept as always, and then we've got a centered close value. These are the probabilities of producing a correct or incorrect response, right, for particular items in the experiment, right? So this is discussed in more detail in the textbook, but you've seen this kind of model before. It's just like the button tapping times. Instead of having centered trial ID, we've got a continuous variable close probabilities, and what we want to know scientifically is whether the scientific question is whether the higher the close probability, whether the close probability has an impact on the electrical signal, so the ERP response, right? So we would expect a smaller amplitude for the signal if you have a higher probability continuation. Okay. All right, so the model is straightforward here because we've got an intercept, we've got a slope, and we've got a standard deviation. So I have chosen some priors here that are reasonable for the particular problem we are working with. Remember, the units are microvolts here. We're not doing any transformation because we don't need to. The data are roughly normally distributed, so we can assume a normal likelihood. And these priors are reasonable. How do I know that? Through prior predictive checks. Okay, so I didn't do any of this here, but that's how we decided on these priors for this particular problem. So let's go ahead and fit this model. This is a simple linear model with one predictor. So you've got the prior specification here for BRMS, right? And then we fit the data using the BRM function as usual. Notice here that I did not write 1 plus close as the predictor for the dependent variable, which is the signal, right? I didn't write 1 plus close here, centered close here, and that's because the 1, which represents the intercept, which represents this intercept alpha here, that is understood in our syntax, and that's also true in the BRMS syntax. The intercept is always assumed to be present, so if you don't write it, it's still assumed to be present in the model, right? So this is just an abbreviated form of the linear model. So let's look at the output, right? So we are looking at this short summary function, which is hidden as a function in the RMD file that produced this output. So you would have to load this function to use it for looking at the output. It just strips out this short summary function. It just strips out the irrelevant parts of the output and just looks at the essential parts. So the essential parts for our purposes right now is just the intercept estimates the estimates of the posterior of the intercept, that is the alpha, and the posterior distribution of beta, which is the slope parameter. So here are the intercept and slope estimates, the means, and the lower and upper bounds of the credible intervals. The R hats here are telling us that the chains are sitting on top of each other, so fat hairy caterpillars, right? And these are the diagnostics which tell you that the model is working fine. So the sampler is working okay. The sigma parameter has an estimate of 11 point something, and a 95% credible interval is shown. So these are the summaries, that would be important to report in a paper if you were doing such an analysis. This analysis is obviously wrong for these data because we have repeated measurements from each subject and each item in this data set. So we're going to fix this model soon. Now, one thing that you can look at if you fit a simple linear model. So what I just fit here with BRM, this is just a simple linear model. It corresponds to the LM function in the frequentist framework, right? So I just for reference, I also fit the frequentist model here to show you what it looks like. And if I were to look at the estimates of the intercept and slope and the standard deviation, they would be pretty similar to these numbers here. Okay, so there won't be much difference because we have a lot of data, relatively speaking. And so the likelihood is going to dominate. So the maximum likelihood estimates and these estimates are going to be pretty similar. Anyway, but what I wanted to show you that's really important to understand from the frequentist perspective is that you can actually extract the residuals from the frequentist model. And once I've extracted the residuals, from the frequentist model, I can look at the autocorrelation function, which tells me the correlation between the residual terms. So the residuals is a vector of the deviations around those alpha and beta predicted values, and those residuals should be uncorrelated. And if they're uncorrelated, the autocorrelation plot will show you that for lags starting with 2 onwards, the correlation will be close to 0, right? This is a scenario that what we are seeing here is the correlations between every data point and every other data point with a lag of 2, 3, 4, 5, 6 in the residuals vector. And if they are uncorrelated, as they should be, right? The residuals are assumed to be uncorrelated. We should see a correlation of 1 for a lag of 0. So every data point is correlated with itself, but every other lag should be close to 0. And indeed it is here. So this is not a terrible model actually, even though technically it's incorrect for these data because these are repeated measures data. It's still not really bad. But I'll show you some more examples later on where the ACF function will show you that the residuals assumption of independence of the residuals is being violated in the data. I'll just show that to you. Okay, so this is the so-called fixed effects model. Okay, so it's called a simple fixed effects linear model because we've got this average effect alpha and then the effect of close, which is represented by beta here. So these are just representing averages here. So that's why it's called a fixed effects model in the frequentist world, right? Now you could go to the other extreme. So in this data, what we have is multiple measurements from multiple subjects. So what you could do is that take the data of each subject independently, fit a linear model on each of the subject's data, and then compute. If you have, let's say 50 subjects, then you would have 50 linear models that you would fit. Okay, so this is what we are doing here. What we are writing here is that we are modeling the signal, the dependent variable, as coming from a normal distribution, but what has changed now is that the alpha and beta represent the alpha and beta for each individual subject separately. So this syntax that you're seeing here, this is something new. We are using Andrew Gelman's terminology here. So this is how Andrew Gelman uses, represents individual subjects' data. And it's very important to understand what this syntax actually means. Okay, so in the data frame, what we will have is a subject column, we will have a C close predictor variable, right? So they'll be continuous variables, and then we will have the N400 signal, which is the dependent variable, right? So that's what the data frame looks like. It has, let's say, 3 columns, and so we might have repeated measurements, from subject 1, multiple measurements from subject 1, multiple measurements from subject 2, etc. Okay, so that's what the data frame looks like. There are some continuous values here, continuous values here. So this syntax here, the syntax that I'm showing you, let me write it here. Subject square brackets n. What this syntax means is that, first of all, n, lowercase n, represents the row ID in the data frame, right? So for example, if the row ID were if the row ID were 1, right? If n is equal to 1, that's representing this row in the data frame. All right? So what this syntax means is that I look up the subject column and look at the row ID number 1 and look at the contents of the data frame in this first row ID. And so when n is equal to 1, so in the situation where n is equal to 1, I'm looking at the first row, in the subject column in the data frame. And so this, you can think of this as a function. And what this function is returning to us is the number 1. It's telling me which subject I'm talking about here. Okay? So that's the syntax that we're using here. So what we're going to do now is we're going to fit a so-called no pooling model. So I'm using Andrew Gelman's terminology here from the Gelman and Hill textbook in 2007. So what's going on here is that we are going to fit a separate linear model for each subject, but each of the intercepts and slopes for each of the subjects has the same prior defined for it, because we have no reason to assume that every subject has different priors. So the model itself is pretty straightforward to set up. The priors are clear, you know how that works. We've got these priors for the intercept, slope, and the sigma. And remember that for sigma, we always have a truncated normal. Even though we write an untruncated normal here, it is understood in BRMS that sigma, all standard deviation parameters, will have truncated priors for them if they're defined as untruncated, normal distributions or the like. In any case, so the model itself, there's something new here that I have to explain. So first of all, notice that I've got a 0 here. 0 indicates that we are not going to fit a grand mean alpha intercept over all the subjects. That's what we did in the fixed effects model. There, we had a single intercept for all participants. Okay? So in this model, we had a single intercept for all participants, and that's represented with a 1 in our syntax and also in BRMS syntax. So what we are doing here is we've got no intercept, no grand mean intercept. Instead, we're going to have a separate intercept for each subject, and that's achieved by relabeling the subjects column, which is numerical values for each subject, as a factor. So instead of treating the numerical values that represents each of the subject IDs, we convert it to a factor type so that it's no longer a continuous, no longer interpreted as a continuous value. And then we are estimating an intercept for every subject now. Okay, that's what this syntax achieves. And this interaction term between the factor version of the subject IDs and the centered close, this interaction achieves the effect that we fit a separate slope for each subject as well. Okay, so this is just a syntactic detail in that we are setting up in order to fit a separate model for each subject. Of course, if this looks complicated, think about it conceptually. It's a very simple situation. You could imagine taking the entire data frame, subsetting the data for each subject one by one. Okay, this would be very clunky, but it's doable. You subset the data for each subject one by one and then fit a linear model on that. That's what we're doing here, okay, in one shot. Okay, so once you fit this model, what you will find is that if you look at the results of the model fit, let me just go down here. Okay, so if you look at this is, I'm skipping over this code because this is just standard summary statistics over the output. But what's interesting in this kind of no pooling model, it's called no pooling because we are not pooling all the data like in the fixed effects model. We are fitting every model separately for each subject. So for example, this subject here has this positive estimate for the slope parameter and a certain credible interval around it, right? So on the, if you look here on the x-axis, we've got 0 here, and these are all positive values, and they are negative values for the effect of close, right? Of close, the slope parameters, possible values. This black line is representing the overall effect that we estimated in the grand mean in the fixed effects model that I first fit at the very start of this lecture, right? With a 95% credible interval around that grand mean. That's that black line, the grand mean, and the broken vertical lines are the 95% credible interval over the grand mean slope intercept, the beta parameter over all the participants, right? But what you're looking at in this plot is separate estimates for each subject. And you can see that there's interesting individual differences between the subjects. So some subjects are positive, some are close to 0, some are negative. Okay? So there's each of the subjects behaves somewhat differently. They don't all show the same behavior as the grand average behavior, right? That is pretty clear, and that's usually true. There will be individual level variation between the participants, right? And you can characterize that by fitting such a no pooling model. And in fact, as a side note, in the old days, and by old days I mean in the 1990s, for example, what people used to do is they used to fit such a model, separate linear models for each subject in repeated measures data like this, extract the estimate of the slope for each of these subjects. Okay, so that would be a vector of slopes. If you have 50 subjects, then a vector of 50 slopes, and do a one sample t-test on that to check whether there's evidence against the null hypothesis of no effect of close. Okay, so that's how people used to do analyze repeated measures data back in the 90s. This was called, or this is called repeated measures regression. Okay, but we are not going to do that. We are going to fit hierarchical models. So how do we do that? Okay, so then now we come to the situation where we want to take into account the fact that different participants behave differently, both on the intercept and on the slope. So graphically, the situation is going to look like this. Let me just create some space here. So graphically, the situation is going to look like this. I'm going to assume that. So first, let me draw the fixed effects model. Okay, so I've got C close as my predictor. Okay, and I've got the N400 signal as the dependent variable. So in the fixed effects model, I had something like this. So I'm just drawing it in the abstract, not caring about the numbers or anything. This is one intercept, right? So if this is the 0 value for close, this represents the grand mean intercept alpha, and the slope of this line, which I'll represent like this, the slope of this line, which is what our beta parameter is, right? The slope of this line is the estimate from the fixed effects model. That was our fixed effects model. The second model that I fit was the no pooling model, and the no pooling model fit a separate line, separate linear regression for each participant, right? So what was happening was that I might have, for subject 1, I might have this line. For subject 2, I might have this line, and so on, right? So there will be different lines for each participant. So what we are going to do now is that we are going to fit a model that has the characteristics of both these two extremes, the fixed effects model and the no pooling model. So we'll fit a hybrid model that has both these properties. It will take into account the grand mean average effect as well as the individual level differences in the intercept and slope for each participant. That's what varying intercepts and varying slopes or linear mixed model is. The way this model works is as follows. So let's take a look at this model in BRMS syntax. We first define the priors. So you just take these priors and write them out here. The important thing to notice here is that we've got the intercept and slope priors. You've seen that before. The sigma is also clear. You've seen this before. The new syntax for defining varying intercepts and slope priors comes here in these two lines here. What's important to note is that we make a distinction in BRMS between sigma, which represents the residual standard deviation, and SD. This is a reserved word, right, which represents the between participant variability. So tau u1 and tau u2, right? So you have to be careful about distinguishing between sigma and SD. When you're talking about the between participant standard deviations, you will use SD. You can also specify, and of course you should specify, whether you're talking about the intercept adjustments or the slope adjustments, and specify which grouping variable we are talking about here. So right now we are looking at between subject variability. So the group is the column subject in the data frame. So this name has to refer to what grouping variable you have in the data frame. This is important because very soon we're going to also have intercept and slope adjustments for items as well. Because in standard Latin square designs, you're going to have repeated measurements not just for subjects, but also for items. So we're going to take that into account later on. And the rest of the syntax is pretty straightforward, right? So we fit the model, right? Here's the BRM model. You got close, and this syntax is again new for you. So this is a new part in the model. What this model is saying is that I want to have a separate intercept. Remember, the one in the intercept, representing the intercept is always implicit. So if I just write C close, I'm assuming an intercept there. So there's going to be a separate intercept and a separate slope for close by subject. So that's what the vertical bars represent. And the double vertical bars, they come from LME4 syntax. These represent the assumption that the intercept and slope adjustments are not correlated. So I just want you to cast your mind back to the bivariate distributions lecture in chapter 1. This is where it becomes important, right? So what's happening in this model is that we have separate intercept and slope adjustments here, but what we are assuming is that the intercept and slope adjustments, they are coming from a bivariate normal distribution. This is the assumption in the model. Okay, so we've got a bivariate U1, U2, bivariate normal distribution. So I'll write it like this, just like in chapter 1, because there are two dimensions, I've written 2 here. The means are 0 by assumption. Okay. And here I would have a variance covariance matrix. Okay, and what does this variance covariance matrix look like in this model? It looks like the following. So I'm going to write it here. This big sigma, this variance covariance matrix, contains in the diagonals the tau u1 squared and the tau u2 squared, right? So these are the variances of the two random variables u1 and u2. And in the off diagonals, this model is assuming zero correlation. So zero covariance, right? And therefore zero correlation. So the fact that I'm assuming zero correlation between the two random variables u1 and u2 is being expressed in the R syntax with this double vertical bar here. Okay, it's a very weird syntax, I admit, but it's convenient. You know, as long as you know what it means, it's easy to understand what it's telling you here. So the double vertical bar syntax assumes zero correlation between the random variables. It's actually very useful to always maintain a graphical summary in your mind of what we are talking about here. Because looking at these mathematical equations, the syntax of BRMS or LME4, and looking at the mathematical formulation of the model, one often forgets, or it's hard to keep in your mind what this actually means, right? And it's easy to keep this in mind if you just think of the graphical relationships that we are modeling. So just to remind you once again, at the risk of sounding really repetitive, right? So what I'm talking about is that I've got a grand mean, intercept, and slope, right? And I've got adjustments around this intercept and slope. And so for every subject, I've got separate intercepts and slope adjustments, right? That's what the U1, U2 are doing. But in this model, I'm also assuming that the intercept and slope adjustments, which we could represent as another plot here. Okay, I could represent this as another plot. Here are the U1 adjustments, the intercept adjustments. Here are the slope adjustments for each of the subjects. We are assuming that these are uncorrelated. So if I were to plot them, they would be just a blob, a circular blob with no correlation. That's what it means to have a variance covariance matrix that has tau u1 squared along the diagonals, the variances of the two random variables on the diagonals, right? And zero correlation on the off diagonals. This is the important point I'm trying to get across. So keep these two pictures in your mind when talking about and thinking about the assumption when you write, let's see, C close double vertical bar subject. This is the scenario that we are actually assuming, that there are varying intercepts and slopes by participants, but the correlation between the varying intercepts and slopes is zero, is assumed to be zero. One other thing I want you to notice in this model specification, which I have over here, is that for the intercept and slope adjustments, I have defined priors, right? So what's going on here is that the intercept and slope adjustments are parameters in the model that represent the individual level differences in the behavior as regards, not the behavior here, individual level differences as regards the ERP signal. So this prior specification here serves a very important function, and that function is to regularize the estimates, the posteriors of each of these parameters. Remember that for each subject, there will be a separate posterior distribution for the U1 parameters. For each subject, there will be a separate posterior distribution for each of the parameters, so each of the U2 parameters. So if you had 50 subjects, how many parameters do you have in this model? 1, 2, that's alpha and beta, and sigma is 3. Then I have 50 plus 50, 100. 103 parameters plus 2 more, so that's 105 parameters. In this simple model, there are 105 parameters. Okay, so the sampler is searching 105 parameter space to figure out the joint posterior distribution of all these parameters. In such a simple model, there are so many. So the interesting issue here that will arise is that the posteriors for each of these U1 and U2 parameters is going to be regularized by these priors here. What that means is that if you have sparse data from a particular participant, Let's say you lost some data, or something went wrong with the computer and you got only a few data points from that subject. Now you have very little data, but you have this regularizing prior available in the model. And what will happen is that the posterior for that subject with sparse data, the posterior will be informed largely by this prior. Just like in the Poisson gamma case that we saw earlier, just like the beta binomial case that we saw earlier. Remember that the posterior is a compromise between the likelihood and the prior. And so if you have very sparse data, then the posterior is going to be influenced by the prior. And that influence of the prior is serving as a regularizing function, in that it basically drags the estimate towards the prior. That means towards normal 0 and whatever tau u1 is estimated to be. And what that implies is that for that one particular subject that has sparse data, the estimate for that subject will be dragged towards the grand mean, because the mean of each subject's adjustment will be dragged towards 0. Why? Because we have sparse data. We have sparse data from that subject, so the posterior mean will be close to 0, and therefore the estimate for that subject will be alpha plus something close to 0. So what's going to happen is that whenever the data from a particular participant is sparse, the estimate for that participant will be dragged towards the grand mean estimate. Okay, and this wonderful property of the hierarchical model is called shrinkage. It's wonderful because when you have almost no data, what information can you get from all the data that you have that would tell you something about that particular individual, even though you don't have much data from that individual? Well, it's the average behavior of all the participants that you have. So when you have little data from one subject, the posterior for that subject will shift towards the grand mean estimates, and that's called shrinkage. And I'm just going to show you graphically what that amounts to. Okay, so we fit the model. It's all standard, nothing special going on here, right? So we've all seen this before. What is interesting to look at is the main parameters that are of interest usually when you're reporting the results. So you have the intercept, and this is the intercept and slope parameters, the grand mean, intercept, and slope parameters, the subject standard deviation for the intercept, the subject standard deviation for the slope. This is the tau u1, tau u2 posteriors, and the sigma estimate. So these are the 5 parameters that you could call the main parameters in the model. You're not seeing the individual level posteriors here, but they are there in the model. You could extract them and plot them, right? So instead of showing 5 parameters here, I could be showing you 105 if there were 50 subjects. Okay, so but there are that many parameters in the model. So what I want to show you next is that the posteriors for each of the subject's slope parameter. Okay, so by subject adjustments to the slope in microvolts. So what we are seeing again is from the hierarchical model, I have extracted the posterior distributions of each of the subject slope parameters, and I'm plotting them now side by side. You can see that some are positive and some are negative, some are close to 0. So now we are characterizing the individual level variation between participants in the effect of close on the ERP signal. Okay? So this is to appreciate what these numbers actually are telling you. I want you to compare. This is just code. I don't need to talk about this code because this is just producing the figure that I'm showing you here. What I'm showing you now is a comparison between the no pooling model estimates for each subject, where we fit the model separately for each participant, and the hierarchical models estimates for each subject. So that means the shrunken estimates from each subject. And so what I want you to appreciate is that the no pooling estimates are actually have much larger magnitudes than the hierarchical estimates, which are shrunk towards what? towards the grand mean. The estimates for each subject is shrunk towards the grand mean slope parameter for the effect of closed probability, right? So that's the effect of shrinkage that you're seeing here. So what will happen is that the estimate from the hierarchical model for each subject's effect of closed probability will be slightly shrunk towards the grand mean beta parameter slope. And it will be shrunk even more towards the beta parameter slope if you have sparse data from that subject. Conversely, if you have a ton of data from that subject, then the no pooling estimate and the hierarchical estimate will be very close to each other, right? So this is a very important property of linear mixed models or hierarchical models, shrinkage, right? And this is one of the important advantages of using a hierarchical model, because unlike ANOVA, repeated measures ANOVA and stuff, where you have to do all this crazy stuff like the greenhouse Geyser correction and so on, when you have imbalance in the data, or you just delete the data where you have some missing data points. That kind of stuff is what we used to do before we knew about linear mixed models. All that stuff is irrelevant for us now. If you have imbalance in the data, the regularizing priors are going to take care of it for you by shrinking the estimate from the sparse data from a particular subject towards the grand mean. Okay, so that's a great property of the hierarchical model, and it's a very valuable property, because if you're studying individual differences, then you're going to get conservative and more reliable estimates for individual level behavior, because the model is taking into account not just the individual's data, like in the no pooling model, but also the grand mean estimates, the alpha and beta parameters, to decide on a compromise for the posterior for each of the participants' estimates for the intercept and slope adjustments. Very, very important property of hierarchical models, and a game changer for us if we are studying individual differences. Or even if you're not studying individual differences, the between participant variability is being estimated for you by the tau parameters, and the within participant variability is being estimated for you by this sigma parameter here. Okay, so what we are doing is we are able to partition the sources of variance in the model between and within in a single model. Very powerful tool. And this is why the hierarchical model is such a useful tool for data sets where you have repeated measurements. The next type of hierarchical model I want to talk about now is the varying intercepts and varying slopes model with correlation. So what changes now is that we are going to assume not only that that subjects' intercepts and slopes vary about the grand mean alpha and beta parameters, but also that the intercept and slope adjustments are correlated with each other, potentially correlated with each other, right? So this is a bivariate distribution now of intercept and slope adjustments. The sigma u, big sigma u here, is this variance covariance matrix that I introduced in chapter 1, and you should perhaps go back and review the section on bivariate and multivariate distribution in chapter 1 at this point, in order to refresh your memory about how these kinds of distributions arise. So here in the off diagonals I've got the covariances, and this correlation parameter is the parameter that represents the potential correlation between intercepts and slopes, right? So everything else is pretty much the same as before. There's nothing new here, so I've not written out all the priors for all the parameters here, just to save some space. Now, one important development in this model is that because we are assuming a correlation between the intercept and slope adjustments for subjects, we're going to have to define a prior on the correlation parameter. Now, in STAN, there is a probability density function called the LKJ prior, which takes one parameter, the eta parameter, which which provides us with a very convenient prior distribution for correlations. So the LKJ prior is usually defined on the correlation matrix. Not usually, it's defined on the correlation matrix. And what that means is that, if you're talking about the variance covariance matrix here, right? So the variance covariance matrix can be decomposed into the following product of matrices. So this matrix here, which is tau u1 squared, tau u2 squared on the diagonals, and the covariances on the off diagonals, could be rewritten like this. So I could write tau u1, tau u2 multiplied with a correlation matrix, also square matrix, with rho u on the diagonals, on the off diagonals, sorry, and finally we have the tau u1, tau u2 standard deviations, okay, in the last matrix here. So if I multiply these guys out, I'm going to get this matrix here. And so this matrix here, this is the decomposition of our variance covariance matrix, okay. So this matrix here is called the correlation matrix, and this correlation matrix will have defined for it in Stan a so-called LKJ prior, and this prior takes a parameter, a numerical value, and we will usually use the parameter value 2. So what the LKJ prior on the correlation matrix implies is that we are going to assume a certain distribution ranging from -1 to +1. When we set the eta value to be 2, that's the parameter that goes into the LKJ prior, what we are assuming is a regularizing prior on the correlation parameter. And what that means is that the -1 and +1 values are downweighted a priori, so they're unlikely to be, they're assumed to be very unlikely, and the more likely values lie in some intermediate range between -1 and +1. Of course, if you change the eta value to different numbers, you'll get different prior distributions. Eta equal to 1 will give you a uniform distribution between -1 and +1, and eta equal to 4 will give you a tighter distribution, right, centered on 0, and so there are other possibilities as well. But in almost all the modeling that we are going to do, not almost all the modeling that we're going to do in this book, we are going to use LKJ prior on the correlation matrix such that we have this kind of regularizing shape. So we will always use eta equal to 2 in our models. This kind of prior is very useful for the correlations, for the correlation matrix, because what it does is that whenever you have sparse data and you're not able to estimate the correlation parameter, what will happen is that the posterior for the correlation parameter or parameters will back off to this prior distribution. So it will be centered near 0 with a lot of uncertainty around it, right? So if you have sparse data, then you don't learn much from the data, and the posterior backs off to this prior, which is a very useful thing to have in a situation where you can't estimate the parameter, but you still want to include it in the model, because in theory, in principle, there could be a correlation, and so you want to know if the data can tell you something about that potential correlation. All right, so that's how we will write the correlation parameter. So here I'm being a little bit sloppy in that I'm talking about the LKJ correlation parameter, correlation prior, as being defined on the correlation. It's actually defined on the correlation matrix, as I said earlier. Okay? So I'm just being sloppy here, but this is the prior on the correlation matrix. All right, so here's the definition of the prior specification. Now the only interesting thing here that should be new for you is the LKJ prior on the correlation matrix. So let me see if I can find it here, right? So here you see the LKJ prior. We are defining the prior to be on the grouping variable subject here. Okay. So if we had another variance covariance matrix for items, for example, and that's coming up very soon, then you will need one more LKJ prior for items. Okay, so that's coming later. So the model looks like this now. It's just the same as before, except there's one more change now, and the change is that instead of having those two vertical bars, you know, which represent the absence, the assumption that there is no correlation between the varying intercepts and slopes, we have a single vertical bar. This is LME4 syntax. So now we are assuming a potential correlation. So the key difference between, you know, the no correlation model and the correlation model is that the no correlation model assumes zeros on the off diagonals, and the correlation model assumes that there could be a non-zero value in the off diagonals. Right? That's the important difference. Okay, so the output of the model you can summarize in the usual way. I'm not going to discuss these parameters. These are all the standard, you know, parameters that we've already seen. Now, the next model that I'm going to show you is going to elaborate on this idea even further. And what it does is that we are going to have not only adjustments to the intercept by subjects, but also adjustments to the grand mean intercept alpha by items as well. So all that's happening is that we've added one more term for the intercept adjustments by items and one more term in the slope for the items adjustments as well. So what this is saying now is that we are assuming an average intercept and slope across all the subjects and items, but for subjects we are assuming some different, possibly different intercepts and slopes, and for items as well. Okay, so the items could also vary, so we allow that possible variation as well. So the model now looks like this. Again, I'm eliding the U1, you know, the well, actually, I'm not eliding anything. So what you have now is a model with varying intercepts and slopes by subjects and varying intercepts and slopes by items. So you have two variance covariance matrices, right, which are written out here. And so now you have to define the priors on all the parameters that are involved here, right? So you've got the alpha, beta, sigma parameters. You've got the tau u1, tau u2 parameters, that's 5. Then you've got the tau w1, tau w2 parameters, that's 7. Then the two correlation parameters and 9. Right? So we have a total of 9 main parameters, but you have to also remember that the intercept and slope adjustments, these guys, for subjects and for items, these are also parameters in the model. So they will also have posterior distributions defined on them. So the priors for the intercept and slope adjustments for subjects and items are these bivariate distributions. Okay. Okay, so that's the full model now, and here's the definition for this full model. You can see the R syntax. I don't think I have to explain anything here because it's all just extensions of what we've seen already. The actual model specification is pretty straightforward with a single vertical bar for subjects and for items now. So this is a new term in the model, and the output now will show us the results. So we can look at the output here, and what we see here in the printed output, this is the entire output here. First of all, the fixed effects, intercept and slope, right? Then by subject, we see the estimate of the standard deviation for the subject adjustment. That's tau u1 estimate. That's the tau u2 estimate with 95% credible intervals. And there's the, sorry, I made a mistake there. The intercept and slope standard deviation estimates. This is the correlation estimate, right? And you can see that the correlation estimate is 0.13, and the 95% credible interval is minus 0.63 to plus 0.79. That is a very broadly spread out posterior distribution on the correlation parameter for subjects. So what that's telling you is that there's a lot of uncertainty about that estimate. And because it spans both negative and positive values, the reason it spans such a broad range of values is because we have sparse data, relatively speaking, and as a consequence, this posterior, which is expressed here through this 95% credible interval, is being influenced by the prior. So here you see that LKJ2 prior's influence here. That LKJ2 prior is basically serving as a regularizing prior here to give you a smoothened out posterior distribution with high uncertainty. Why high uncertainty? Because we have very sparse data. We can't really conclude much about the correlation between the intercepts and slopes in this sparse data set. That's the subject parameters, and then there will be item parameters as well over here, right? These are the item parameters, the standard deviation estimates, and the correlation. The correlation here is minus 0.41, but if you look at the range, the 95% credible interval, again you see that the data were very sparse, did not really allow us to estimate that correlation with any degree of precision. So the uncertainty is very, very high in this estimate here. But the model does estimate posteriors for everything, right? So it doesn't give any convergence warnings or anything like that. And so we are able to fit these complex models because of the fact that we have regularizing priors defined on all the parameters here. Okay, so if you were to try to fit this model in the frequentist framework, you would hit convergence warnings, and that would be because you're trying to estimate the maximum likelihood estimates of the parameters, and under sparse data, you may not, the optimizer may not be able to estimate them. So that's why you get those boundary singularity warnings in the frequentist LME4 package. You won't get those kinds of warnings in the Bayesian model because the regularizing priors take care of the situation when you have sparse data. But you also have very high uncertainty on the posteriors when you have sparse data. So the Bayesian approach is actually a very conservative and robust way to estimate the parameters of interest in your model. So these are all the parameters. Now I won't go through each one of them, but you can just quickly eyeball the correlations, you know. So take a look at this correlation, for example, very widely spread out between -1 and +1. So we hardly learned anything from the data there. Okay. But it's good to have that correlation, and that was the famous paper by Dale Barr and colleagues in 2013 in the Journal of Memory and Language. They talked about the fact that it's the most conservative thing you can do when you're fitting these kinds of models is to fit a so-called maximal model, right? That's what they call it in that paper. And what they mean by a maximal model is that you should allow all parameters to be included in the model if in principle those parameters could play a role in determining the posteriors or determining the estimates of interest, right? So that's what they mean by a maximal model. So they're right. Ideally, you should try to fit the most conservative model that you can. In the frequentist framework, you may not be able to do that because of convergence problems. In the Bayesian framework, you will almost always be able to do this because of the regularizing function of the priors in the model. So that's a very big advantage of the Bayesian approach. We just looked at the maximal model in the terminology of Dale Barr et al., where you've got varying intercepts and slopes for subjects and for items, and you assume a potential correlation between the varying intercepts and slopes. But you could go even further. This is not possible to do, what I'm about to show you. This you cannot do using the LME4 syntax in the frequentist models. But in the Bayesian framework, it's possible to extend this model even further and assume that the residual standard deviation, which is the average within subject and within item variability in the signal, is different for each subject. So you could have varying intercepts on the residual standard deviation as well. Okay, so it's called a distributional regression, I believe. And the way this would work is everything else in this model is exactly the same as what you've seen in the maximal model. The only new thing is that for every subject, I'm going to have a different residual standard deviation. And so the way we will set that up is that we are going to have an average standard deviation across all the subjects, so an average residual, but we will allow some variability around that average residual by subject. So that's this adjustment to the average residual standard deviation. And for this parameter here, we're going to define a hyperprior. Okay, and so what we end up with is that we've got a grand mean residual standard deviation, and then we have an adjustment to that grand mean by subject. Okay, and because these adjustments could be positive or negative, right? We can't have a residual standard deviation that's negative, right? You could have positive and negative adjustments here, but what we want in the end to go into this model here is a residual standard deviation that is positive. So what we're going to do is we're going to exponentiate whatever the end result of this addition is going to be. Once we exponentiate that, we are going to get positive only values. So that's why this exponentiation happens here, and this sigma underscore n will be then the residual standard deviation, which will have an adjustment by subjects as well, right? So that's the only new thing here. So there's some hyperparameter defined for this hyperprior and so on. So that's the only new thing in this model, okay? And so if you look at the syntax for having this kind of, for doing this kind of distributional regression, the only new thing is we are going to specify that the residual parameter, right? The residual standard deviation parameter sigma is going to have varying intercepts adjustment by subject, and here's the prior defined on that varying intercepts for the subjects for the residual standard deviation. That's the only new thing in this prior specification. In the model itself, if you look at the BRMS syntax, there is one more thing that you have to write. So the standard model that we have seen so far comes here. After that, there's a comma, and then comes the specification that I'm going to have a fixed effect intercept for sigma, and then varying intercepts by subject, right? So that's the new thing that you would write if you were doing a distributional regression, right? So you can look at the output of this model as well, and you'll see that you will have additional information due to that, the varying intercepts for the residual standard deviation as well. So that's a potentially useful model in a situation where you want to take seriously the possibility that different participants might have different residual standard deviations. So now let's look at another example of a hierarchical model, this time using a log normal likelihood. So the data we're looking at is data from a Stroop experiment. What we have is reaction times to subjects being shown the word green or red or some such color like that, which is written in the color green or red respectively. And that's the situation where the color that the text is written in matches the word that they're actually seeing. And so the Stroop effect is basically the phenomenon that if you change the color of the word of the text, let's say you've got the word green but you write it in red or something like that, then it's harder to actually name that color because there's a mismatch between the color in which it's written and the meaning of the word that you're actually seeing, or the actual color that is being represented by the word. So that's called the Stroop effect. You see a slower reading time or reaction time if the, the text color and the actual word are not congruent. Okay, so that's the Stroop effect. So we could model that by by designing an experiment. We could set up an experiment where we have congruent and non-congruent conditions. So there's two conditions. So these are categorical conditions now, right? You've got either a congruent condition where the color and the actual text match, and the incongruent condition when they don't. And you could have repeated measurements from each subject, right? So standard repeated measures design with two conditions. So this kind of experiment is very common in psychology and in linguistics. So it's good to see how we would analyze this kind of data. So what's different here, of course, is that our predictor, the two levels of the condition factor, congruent and incongruent, these are categorical variables. So what we're going to have to do is we're going to have to code them in a particular way numerically so that we can actually represent the two levels numerically in the linear mixed model, in the hierarchical model, right? So instead of having continuous values like close or trial ID or something as in the past, in previous examples, we are going to have a categorical variable that is coded numerically to represent the two levels of the factor congruency factor. Okay? So our dependent variable is reaction times. Assume a log normal likelihood. Alpha is the intercept, grand mean intercept. The C underscore condition variable represents the congruent and incongruent conditions. So we're going to set it up so that the congruent condition is coded as, I think, as -1, and the incongruent condition is coded as +1, right? Yeah, I couldn't see that text there. So the incongruent condition is coded as +1, the congruent condition is -1. So this column here in the data frame will contain +1s and -1s, right? And the rest is all familiar to you. We have the intercept adjustments, slope adjustments. We can assume a correlation between them, and the rest is all completely standard, except that we are working with the log normal likelihood. Therefore, our priors have to reflect the scale of the parameters, right? So as I discussed in chapters 3 and 4, for the log normal likelihood, I want to have reasonable priors. I'm not going to put a 0, 1000 prior here. That would be a completely insane prior on the log scale, right? So be careful about that. This is a very common mistake that people do. They forget that they're working with the log normal likelihood, and they end up with really wild priors for the parameters. That will lead to convergence warnings. Your model will not be able to get the posteriors, sample the posteriors. So I've chosen a relatively informative prior. Well, it's not super informative actually on the log scale. This is not a very informative prior, but it's somewhat constrained in that it doesn't allow very large differences between the it doesn't allow very large variation to be possible in the posterior distribution of the beta parameter, which represents the Stroop effect, the effect of the congruency or incongruency of the words that are being shown to the subjects. Of course, I'm kind of skipping over some details here. The contrast coding that I've chosen here, this +1 -1 coding is called contrast coding. This is a topic that deserves a lecture on its own, maybe a 90-minute lecture that I will do later on. But right now, I just want to show you that you could represent the two levels of a condition with this kind of coding, which is called sum contrast coding. So this is basically what we are doing is we are centering the predictor because the average of these two would be 0, right? So I will discuss all that later in detail, but it's enough for us to know that we are just centering the predictor by sum coding it to +1 and -1 here, okay? All right, so we define some priors, some reasonable priors for the hyperparameters. So these are my hyperpriors, right, for the tau parameters. And then I have the LKJ correlation parameter. Again, sloppily written for rho u. It's actually for the correlation matrix, but you know what I mean, right, when I write this here. Okay, so we are only looking at correct trials. So when people were able to respond correctly and tell you what the color, the meaning, what the word was that they were seeing on the screen. But as you can imagine, they will be slower to respond when you have an incongruent setting. Okay. So here we are just centering the predicted, the +1 -1 coding that I just mentioned earlier. That's how we are setting it up. And so we have a new column, C underscore cond, which represents the predictor now. So this is different from the previous models that I showed you, because now I don't have a continuous predictor. I have a categorical predictor. This can only be +1 or -1 here. Okay. So everything else is the same, nothing unusual here. I've got intercepts and slope adjustments by subject with correlations. So the specifications are the same as before. Notice that I put iterations equal to 5,000 here. And the reason is that when I try to fit this model with 2,000 iterations, I got some convergence warnings. So the warnings advised me to increase the number of iterations. So I did that. And now I have 5,000 iterations. What that means is I've got 2,500 samples from each chain, and there are 4 chains, right? So 2,500 times 4 is the number of samples that I have from each for each of the parameters in the posterior, right? So you can examine the posteriors yourself. You know how to do that now. You can also do posterior predictive checks and do all those things that you could to evaluate the model that we discussed earlier. So the only thing I want to show you here is that the main thing of interest in this model was the effect of the congruency on the reaction times. You can see that the estimate on the log scale is 0.02 with a 95% credible interval. You know, that's shown here. And so that's useful information. What that tells me is that the result is consistent with the belief that incongruency will lead to slower reaction times, right? We haven't done any hypothesis test here. We are just describing what we've observed in the posterior distribution. The pattern, which is mostly a positive distribution for the slope parameter, the beta parameter, is consistent with the prediction that you will get slower reaction times with incongruent conditions. Okay, so that's an example of using the hierarchical model with a log normal likelihood with varying intercepts and slopes and a correlation. You could always back transform the beta parameter estimate, which is hard to interpret on the log scale. So you could back transform it to the millisecond scale using the methods that I showed in chapter 4. And what you can do with the Bayesian approach, which is very, very convenient once you've done the back transformation, is that you can actually display the posterior distribution of the estimate on the millisecond scale. So you not only have an estimate of the Stroop effect, the effect of incongruency, but you also have a measure of the uncertainty of your estimate. That 95% credible interval on the posterior of the beta parameter is telling you how unsure you are about the Stroop effect given the data and the model that you have, right? So that's one of the really big deals about Bayesian modeling. Bayesian modeling is all about uncertainty quantification. I'm not only interested in what the average effect, the Stroop effect is. That's this average effect. That's just a point value. I'm also equally interested in how uncertain I am about that estimate. So for example, in one experiment, if I get an estimate like this, which is very widely spread out, I have a lot less information about the beta parameter than the situation where I have exactly the same point estimate, but a very tight posterior, right? So these two situations are giving me very different information. The first, broadly spread out posterior, is very uncertain, but the second, tightly spread out posterior is giving me a lot more information because I have a heavily constrained posterior on beta. And that would happen if I had a lot of data. Assuming the priors that I've used, if I increase the amount of data, I would get tighter and tighter estimates of the posterior of interest, which is very informative for me. If I, as a scientist, if I'm interested in getting as precise an estimate of the Stroop effect as I can, it is in my interest to try to get a tight posterior. And the way I would get that, given the priors that I've set out, which are not too informative and they shouldn't be in the normal case, I would need more data than what I have to be able to get such a tight posterior.